Factoring by special products are basically shortcuts. If you notice that a trinomial falls into a particular pattern, this is going to be a quick way to factor them. So if we have a squared plus 2 times ab plus b squared, this will always factor in a particular way. A squared will always factor to a times a, and b squared always factors to b times b. Now our middle terms, a times b and b times a, are really just ab and ab. So assuming that both of these are addition, ab plus ab is 2ab. So a squared plus 2ab plus b squared always factors to the perfect square, a plus b times a plus b, or just for shorter notation, a plus b squared. The same thing is true for a squared subtract 2ab plus b squared. A squared factors to a times a, and b squared would factor to b times b. If both the operations are subtract, we have a negative b times a negative b for a positive b squared. And then our middle terms, our outside and inside, will give us a negative ab plus negative ab, which is our negative 2ab. And so a squared subtract 2ab plus b squared will factor, shorthand notation, a subtract b squared. I'm not particular if you like to write it as a subtract b squared or simply a subtract b times a subtract b. Another good one to know, and this is nice whenever you have only two terms in your that you're trying to factor. So this would be a binomial rather than a trinomial. A squared subtract b squared. Again, a squared would factor to a times a. B squared factors to b times b, but since we want to subtract b squared, we need a plus b subtract b. So we get a positive b times a negative b for the negative b squared. And notice what happens in our middle terms here. A times negative b is a negative ab, and b times a is a plus ab. So these two cancel each other out, and we're left with simply a squared minus b squared. So a squared subtract b squared is always going to factor to a plus b times a subtract b. And a note here, if you ever have a squared plus b squared, that's always going to be prime. Don't waste your time trying to factor it. It won't happen. Some examples here. And the way I usually spot these is, does it look like there's a bunch of squares floating around? And at first, the 64 looks like a perfect square, and the 4 looks like a perfect square. But then I've got some extra x's, and a lot of y's floating around here. So I think what I want to try first is seeing if there's some common factors I can factor out. So it looks like 4 is common to all 4 terms, and I've got x common to all 4 terms, but y is not common to all 4. Sorry, all three. It's only common to these 2 terms. So pulling out the greatest common factors, 4x, looks like all I can take out. That'd leave behind x squared, subtract 8xy, plus 4 goes into 64, 1 time for the 4, 24, 16, y squared. So now I have an x squared is a perfect square, and 16y squared is a perfect square. So if it's going to fit into this format, what I'll do is go ahead and take a guess that it will fit into this format. X squared factors to x times x. 16y squared would be 4y times 4y. And then I'm going to check and see if I get the correct middle term to subtract 8xy. Because I want to multiply to a positive 16 but add up to a negative, I want a negative times a negative. That way they'll multiply to positive 16, but my middle terms then, I'll get a negative 4xy and another negative 4xy, which adds up to a negative 8xy. So we can then, just to make things look a little more compact, go ahead and write it as 4x times x subtract 4y squared. Okay, so the x squared subtract 49. Again, whenever I have 2 terms to factor a binomial, I immediately think difference of squares. And I do have that. Let's go ahead, let's expand this out a minute. X squared subtract 49 is 7 squared. So as far as that a squared subtract b squared format, my a is x and my b is 7, and I know this factor to a plus b, a subtract b, which will be x plus 7, x subtract 7. So here I'm using the formula a little more directly. Here I basically did a guess and check. Both methods work. For this example, I have two terms, so I start immediately thinking difference is square, but 12 is not a perfect square and 3 is not a perfect square, but I do have a greatest common factor. So whenever possible, factor out a greatest common factor first, because now the problem's much easier to work with. And again, this is optional, but some of you might like to do this. Whoops. What I want to do is take that 4 and write it as 2 squared. Subtract a squared. And it's nice and clear that I've got an a squared subtract a b squared. And then again, this will factor then to 2 plus a and 2 subtract a. When factoring, the order of the factors does not matter. So 3, 2 subtract a, and 2 plus a is also correct. There's really no difference between the two. A few more examples here. X squared subtract 4x plus 49. Again, this is optional. I have x squared. 14 is 2 times 7x, and 49 is 7 squared. So I have that format of a squared subtract 2ab plus b squared. Now our formula says this will factor to a subtract b squared, or a subtract b times a subtract b, which in this case would simply be the x subtract 7. Alternately, with this one here, again I have the same sort of setup. X squared plus 8x plus 16 is x squared plus 2 times 4x plus 4 squared. So again, a squared plus 2ab plus b squared. And so this should factor to a plus b quantity squared. But I'm going to take a slightly different route. Looking at the x squared, I know that factors to x times x. Looking at the 16, I know 16 is going to probably factor to 4 times 4. Since it's a plus 8x, I know I want both of these to be plus, so I have my x plus 4 quantity squared as my factored form. So I can get there straight from the formula, or I can always fall back on doing our guess and check or grouping method. And then this example here, I've got two terms, so I start thinking maybe it's a difference of squares. And again, I can think of this as 2y all squared, and then 81 is 9 squared. So this should factor to the 2y plus 9 and 2y subtract 9. Okay, so again, some people prefer to factor just using the techniques that we've been using in 5.6 rather than memorizing the formula, but that difference of squares, a squared minus b squared formula, that one we use so often. I would really encourage you to memorize this one. And it's so simple. Okay, so in the book, there's a nice factoring strategy laid out, but we're skipping the cubes. You don't have to worry about that part of it. And we've got it here. So general strategy, always first thing, are there any common factors? If so, factor out the greatest common factor. So get any greatest common factors out of the problem. That makes the numbers much smaller, easier to work with, and takes a lot of stress off of us. Next thing to think about is how many terms are there in the polynomial. If there's two terms, so that's a binomial, decide if one of the following formulas may be used. So in particular, the difference of two squares, the a squared minus b squared, then we can use our a plus b, a subtract b formula. And then in the book, they'll be talking about the difference in sum of two cubes. We're skipping those problems. You don't have to worry about them. Then there's our usual case. If there are three terms, if we're factoring a trinomial, try one of the following. We've got the two formulas, the perfect squared trinomial, a squared plus 2ab plus b squared, and a squared subtract 2ab plus b squared. But if it's not a perfect square, you either do the trial and check method or the grouping method. If there are four terms, again, try the factoring by grouping. This one, pretty easy to do, but everyone seems to forget when it comes to the test that you can factor by grouping. So just keep reminding yourself if there's four terms, factoring by grouping. Once you have factored a problem, sometimes you can take them a little further. Sometimes your factor will still contain a perfect square that you can take a little further.